This is a short video overviewing stoichiometry in the mole-to-mole conversion process. So what is stoichiometry? Stoichiometry is using a balanced chemical equation to allow us to determine an unknown quantity of product or reactant from a known quantity of product or reactant in the system. So it allows us to predict the outcomes or the necessary reagents in a system using that balanced equation that we learned how to do in one of the earlier videos. It's essential that you understand how to balance an equation before you move on to stoichiometry. So if you're still struggling with that, I would suggest going back and reviewing the how to write a balanced equation video that was published earlier. So let's start with chemical equation we've looked at a lot. This is the combustion of acetylene. It's the one we used when we were talking about balancing an equation. So C2H2 reacting with O2 to produce carbon dioxide and water. What does this mean? Because we learned how to balance an equation, but stoichiometry gets into what is that balanced equation actually referring to? Well, the important part are the coefficients in front of the compounds in the balanced equations. Those numbers that we use to balance the equation represent molar ratios between the different components of the system. And that's the important part. We're talking about moles here. So we can make a ratio between any two components in the system. For example, we can look up here and see that for every 2 moles of acetylene burned, we produce 4 moles of carbon dioxide because there's a 2 in front of the acetylene and a 4 in front of the carbon dioxide. And that's what these numbers are all about. It's important to remember these numbers are referring to molar values, not grams, not molarity, not liters. These are always referring to molar values. So everything about stoichiometry is going to have to come back to moles at some point. So why is that ratio important? Well, if you remember back to when we started talking about dimensional analysis, we use the term ratio a lot. If I can make a ratio, if I can say I need X amount of compound A to produce Y amount of compound B, I can create a dimensional analysis ratio. So I can create a part of a longer dimensional analysis calculation. For example, using our same equation, if I ask the question, how much water vapor is generated by using 2.4 moles of O2 to burn excess acetylene? I can answer this through a very simple one-step dimensional analysis. My known is the oxygen. I know I have 2.4 moles of O2. My unknown is the water vapor. So I'm looking at the ratio between water vapor and oxygen. So when I look at that, I'm like, okay, well, oxygen has 5 in front of it, water has a 2 in front of it, but how do I convert that into a dimensional analysis? Well, the dimensional analysis is always the coefficient of the unknown over the coefficient of the known. So since it's 2 moles of H2O, which is my unknown, per 5 moles of O2, which is my known, it would be 2 over 5 as my ratio. So I would set up a very simple one-step dimensional analysis. 2.5 moles of O2 times 2 moles of water over 5 moles of O2. Moles of O2 cancel, leaving me in moles of water, which is what I want to be in. So I would then do 2.4 times 2 divided by 5. Give me a final answer of 0.96 moles of water. So I could say for every 2.4 moles of O2 used in excess acetylene, I would produce 0.96 moles of water. Let's try this one more time. So we've got acetylene again, same equation. Now let's look at it in terms of, all right, how many moles of acetylene will I burn to get 3.4 moles of CO2? So now my unknown is a reagent. My unknown is the acetylene. My known is one of the products, the carbon dioxide. Doesn't change how the ratio works. It's always the coefficient of the unknown over the coefficient of the known. So I would look at the coefficient in front of CO2, which is 4, and the coefficient in front of acetylene, which is 2, and I would set up my dimensional analysis. 2 for acetylene over 4 for CO2. Moles of CO2 cancel, leaves me in moles of acetylene, so 3.4 times 2 divided by 4. You could reduce the ratio to 1 over 2. Doesn't change the math in any way, shape, or form. I just tend to always keep the coefficients that are in the balanced equation so you can see that one-to-one connection between them. That means to produce 3.4 moles of CO2, I would have to burn 1.7 moles of acetylene, according to our system. So when we do stoichiometry, we're always doing this 5-step process. 1, always have to determine a balanced equation first. 2, convert any known values into moles. Remember, a balanced equation is always based on molar values. So whatever system I'm working in, I have to get it to moles eventually. We're going to address that in the next video where we talk about mass to mass conversions. Today, we kind of skipped over 2 because I gave you the moles to start out. 3, determine the limiting reagent. At some point during your system, you are going to run out of one of the components. That's what we refer to as the limiting reagent. We're going to go into that in a little more detail in about 2 lessons. So after this, you can go look at how we use a limiting reagent video to try to get at that idea. 4, this is what we did today. Use the balanced equation to determine the moles of the unknown value for the moles of the limiting reagent. This is using that balanced equation ratio. You know what your unknown is, you know what your known is. So it's always coefficient of the unknown over coefficient of the known. Process that, it gives you your moles of unknown. And then 5, just like 2, in the real world, we're usually not reporting moles. We're usually reporting something like grams or liters or something like that. So we'll have to do a conversion factor from the moles into our desired unit. So that's a brief overview of how we go from mole to mole conversions in stoichiometry.